Sitting on the table over here, I have a thing of water. I'm going to give you a few numbers that I have measured about that particular thing of water and ask you a handful of questions. Okay? Number one, I'll show you how I did it in just a second. It's not that complicated. But I measured the weight of that water. I should do this first. Okay. I measured the weight of the water to be 18.4 newtons. I have measured the mu of the surface between the water and the table that it's on to be 0.21. We're going to put in a force. Please notice, importantly, that is not currently moving. Okay? Not moving. And I'll just help you with this particular detail. The fact that it is not moving means this thing that I just gave you here is mu s. I will apply a force of 2 newtons. The question is, how much will it accelerate? Go ahead and use that as a bell ringer while I attempt to show some of the calculations of these particular numbers. I have a variety of scales here. This one is on a scale of 0 to 20. This one's on a scale of 0 to 5. And notice, by the way, that they are the same distance. So if you look inside, you'll notice that the reason that they're different scales is because there's entirely different springs in there. There's probably something to be said there about K, but we'll let that. Okay. And then an even larger spring over here, although it does give a larger distance, much larger spring because it'll put a lot of force out. Anyway, I have ropes hanging from here. Here I have this rope, okay? Just pulling this straight up into the air. And as it hangs there, this thing hangs at 18.4 newtons. Right there. There it is. That's how we measure its weight. In just a second, I'll use this guy to apply 2 newtons. My question is, what is its acceleration? Give you guys about 3-4 minutes to accomplish that. Yeah, 2 newtons horizontally. Should specify. We'll apply 2 newtons horizontally. All right, let's run through this. Force diagram. Here's my jug. What's my force diagram? Force gravity down. Equal, greater, less? Equal. Friction, which way? What's that? Not up. Yes. Whichever, let's say we're pulling to the right here.
I thought it was just stationary.
Oh, well then there would not be friction if it was just stationary. We wouldn't say. Okay, so let's say force of Spanauer on bottle. Okay? And force friction back. Okay, and which way is it going to accelerate? It's a trick question a little bit there. But let's figure this out. What do you want me to do first? In the why? Agreed. How come?
Because you need to find force.
Correct. Sum the forces in the y. What are the sum of forces in the y?
Force normal on plus minus force gravity.
Minus force gravity. I'm going to stop at this point in time and say this, okay? I yelled at somebody last night. I will apologize to them because they're not in this hour. I'll apologize to them the next hour. But there is one thing that is very, very important in here, okay? You are here for you, okay? I need more questions in this class, okay? I can feel that there are more questions in this class, okay? I think there are those of you, don't get me wrong, who are understanding this completely and you don't have any questions, and that can be intimidating for the rest of you, okay? For the rest of you, forget that, okay? This class, good questions come out of not knowing, okay? If ever I do something up here and you don't personally know how to do it, ask the question. The class as a whole is better when there's a lot of questions. Why? I can answer them usually in 3-4 seconds and help you out. But if you have a question at this point in time, anything that has been done, and you don't ask it, what are we doing here? We're wasting our time. You're wasting your time. You have to learn. And if you're introverted, find a way. Okay? Write down the question, then email it to me later. Or write it down on a piece of paper and hand it to me later. I don't care what it is. Find a way to get me the question. Sum of forces is positive force normal up, negative force gravity down. Is there acceleration on the y? And ultimately, this equation is really just showing you something that you already knew, that these two forces better be equal and opposite. Force normal is equal to force gravity. Now, usually we would use mg. Why are we not going to use mg here?
Because it gives you force of gravity.
Yeah, it already gives us force of gravity. It hasn't given us mass, it's given us the force of gravity. So that is 18.4 newtons. Excellent. What do we do with that force normal and force gravity? Why is that helpful for us?
You're going to find force of friction.
Good. Mu is, by definition, equal to force friction over force normal. That's not usually how we write it, though. We usually write it as force friction equals mu times force normal. So, if mu is 0.21 and force normal is 18.4 newtons, okay, what do you get? 3.1? 3.864, let's go, there's 3.86. All right. Now, you can already potentially see the answer to my question, okay? This is a little bit of a trick question. I wanted you guys to see this right here, because please remember that since this is not moving, since this is static, this is actually force friction static max. We talked about this the other day. So when you have a graph of friction, I've done this example a lot. If you don't quite understand this graph yet, it's very important that you do. Okay, this section over here is static. This section over here is kinetic. Kinetic is constant. It's always the same amount. Who the heck cares? Okay, but let's say I play this out. Like, let's say you don't notice the problem yet. Like, maybe you're not understanding where I'm going with this yet. And so you decide to do the next logical thing, and you sum the forces in the x. Let's just play it out as though we don't see what's happening. What are the sum of forces in the x?
Forces
What's that?
Forces
Force of Spanauer on bottle. Negative force friction. Mass times acceleration. Now, we weren't given mass, by the way, but how would we get it?
Using the coefficient of gravity.
Yeah, Fg equals mg cuts both ways. Fg equals mg, if you have mass, will give you force of gravity. But if you have force of gravity, what simple thing can you do to get mass? Divide by g, yeah. So this is 18.4 newtons divided by g. What do you get? A little under 2. 1.88, okay? Kilograms. So, you come over here and you do your work and you say force of Spanauer on bottle minus force friction divided by mass gives us acceleration. We plug our numbers in. Spanauer said that's going to be 2 newtons. This is going to be 3.86 newtons divided by 1.88 kilograms. And I'm going to stop there because this is a dumb answer. Why is this a dumb answer? What's that? So what does that mean, according to our math, is going to happen? I'm going to pull this way, and it's going to take off going that way. Agree or disagree? Agreed. I'm with you. I strongly disagree. And the reason why this particularly works out comes back to the model of static friction. Comes back to this right here. See, that number, that 3.86, is not how much friction is coming out. That is the maximum. I'll show it to you right now, okay? The reason I know these numbers is I straight up measured them earlier. I'll show you how I measured them. It was relatively easy to do, okay? But watch here. I'm going to go ahead and pull on this. Notice, am I pulling on this? Yes. Is it going anywhere? So it means it's following which law? Which of Newton's laws is it following? First, correct. Okay? It is following first. So what should forces be? Balance. Should they be unbalanced like we calculated over here? No, because that number that we calculated is the maximum. What happens if I only apply 1 Newton here? What should be friction if I only apply 1 Newton here? 1. If I apply 2 newtons, like I said I would, here I am applying 2 newtons, it's on the 2. How much is actual friction? 2. 3.86 is only going to be the answer if you get to that particular maximum. The reason why this is off is because you have to recognize what this number means and have to recognize that actually the math works like this. How much is friction, we said, if I'm pulling at 2? So how much is acceleration? 0. And if you recognize this, you can actually get away with not doing as much work, because did we actually need to know what mass was whatsoever? Yeah, the mass doesn't matter if the forces are entirely balanced. Now, let's talk about how I measured this for the sake of understanding a little bit later, okay? And understanding, hopefully, this graph a little bit more, okay? What I did, first thing I showed you, I lifted this up in the air, okay? And then the next thing I did was relatively simple. Right now, I'm essentially going over what the lab would have looked like tomorrow, just to try to get you a better understanding of kind of what you would be working with right now. It's just simple. I pull, I pull, I pull, I pull, I pull, and then it starts to go. When it starts to go, what I would notice over here is that my original pull will then decrease. Okay? Why did it decrease?
Inertia.
Why did it? There's 2 types of surface friction. What are they?
Static.
So why did it change?
It changed to kinetic.
Because it's moving now, right? So the first number, that 4, is what it took to budget. That's the maximum. Now, we calculated 3.86, and that was just because when I actually did the calculation of mu, I just took 4 divided by 18.4, just the forced friction divided by the force normal in this case, and I got 0.21739 blah blah blah, and I didn't want to use a bunch of those extra decimals, and so I just told you 0.21. I guess I should have technically told you 0.22. That's why we were a little bit off. But what would you do if you wanted to measure kinetic friction instead of static? Static was just look for this maximum number that it took to move it. What would I do instead if during a lab you wanted to measure kinetic friction?
Measure force while moving.
What's that?
While moving.
Yeah, and how do I want to move this to make it as easy as possible?
Constant.
Constant velocity. Right. I just pull it across the front at a constant velocity. I get that it's about 3. I take 3 divided by 18.4, and I get 0.163. That would be the coefficient of mu, or the ratio between the two. Now, those models are not perfect. Ultimately, they take place between these two materials, and understand that there is an assumption that these materials stay the exact same the entire way. There's no like ridges or bumps or sticky or anything in there, because if there was a stickiness, say in this area, from me dropping orange juice sometime last week or something like that, what's probably true of the coefficient of friction in this area? It's greater. It's going to hold on to electrons and protons better, and so it's going to increase. So mu values have to be measured kind of experimentally, because they're they're a little bit vague and all over the place. So again, what I just said a second ago is in my example, when I was moving this jug, I applied a different amount of force, okay? And on this cart, what I found is it took 4 newtons, that's this mark right here, 4 newtons to get it to budge, which is where we got mu static, or force friction static max, over force normal, 4 newtons divided by 18.4. Where kinetic friction is this guy right here, obviously I'm not going to scale right now, and was 3 newtons. So to get kinetic friction, that's just force friction kinetic over force normal, or 3 newtons divided by 18.4. What I wanted you guys to see in this particular example is this. If the object's not moving, and I calculate the maximum is 4, and I pull at 2, how much is friction actually? 2. Correct. Okay? Here's a problem that will definitely be on the test. And I say this every year, this problem will be on the test, and people still miss it. Okay? You've got a giant box that you can't move. Okay? You just cannot budge. How does the friction compare to the force you put, or let's say a giant boulder, okay? Or shoot, this table, okay? This table, how does the friction pushing back compare to the force that I put in? It's equal. People regularly want to say friction is greater. The maximum is probably greater, but the actual amount of friction will always match because of Newton's first law. If I push this a little bit with 5 newtons, how much is it pushing back? 5 newtons. If I rear down, try to shove it with all of my might and try to shove it at whatever all my might is, let's say 20 newtons. Okay, how much is it pushing back? You got the idea. It's always going to equal until it gets to that max. All right, let's move on.
Mr. Spanner.
Yes.
So at what point during pulling the bottle will it be following Newton's second law? Would it be when it changes over?
Excellent question. It's an interesting thing. It's a really good point. Okay, this little ledge right here, because it drops, because friction almost immediately drops, causes there to be a little bit of an acceleration. Like if you're moving something really heavy, you can always see this, because once you finally get a heavy object moving, it lurches forward. The reason why it lurches forward is you press harder, you press harder, you press harder, you're not budging it, you're not budging it, you're not budging it. And now let's say the maximum is 100 newtons and you push at 101. If you push at 101 and the maximum's 100, you have an unbalanced force and that thing's going to accelerate. Not very much, but it's going to accelerate, yes? And if it accelerates at all, is it static anymore? No. So what happens is you're still pushing at this 101 and your friction drops way down, say to, instead of 100 like it was, it drops down to say 80, And now you have a decent net force, which is why heavy objects always appear to lurch forward. They kind of like jump forward when you actually break that particular barrier. You can see this, by the way, if you're ever like pushing like a table, and that noise that comes out when it actually starts to move is because of this particular fact. Got it. So yeah, so it would be, again, with static friction. Now, there is another weird thing with static, okay? There's another weird thing with static. Okay, friction is easy. That's right. Kinetic friction is easy. Just always goes the opposite of the way it's moving. Always, always, always. Static friction goes the opposite of the way the object wants to move. Okay, so in the case of, here, I was pulling it left, friction goes right. If I was pulling it right, friction would go left. But let's say, I think I did this example briefly before. You've got a truck, and there's a box on the back of the truck, and currently the truck is not moving, right? And the truck takes off, and that box is not supported, okay? Is it an issue? Probably. If you go too fast, perhaps. But if the box is heavy enough, you would expect the box to move with the truck. Yes? What would the force diagram be on the box? What's actually pushing it forward? Well, you'd have force gravity down, you'd have force normal up, and what would be actually pushing it forward? Static friction. And you'd say, wait a minute, it's moving. No, no, no. When we say moving, we're talking relative to the two surfaces. Is this surface and this surface moving relative to one another? No. Which way does the box want to go when the truck takes off? Essentially, it wants, well, let's say not want to go, because you're right, this way. It wants to stay put, right? So relatively, it wants to go this way. So which way does friction go? The opposite way. It's the exact reason why, as Yoda sits in my hand here right now, and I take off with Yoda, Yoda will continue this way. Now if I take off, I don't want to break Yoda. I've done this before. Okay? Now if I take off too fast, I've broken the maximum static friction that's necessary, and thus it will not get that friction going that way, and thus, here's another example of it. Your tires on your car rely on static friction, okay? Don't believe me? You actually get to change which way friction in your tires is pointing by steering the wheel. But if friction isn't big enough, right? If, for example, you hit ice, okay? And you can't, what happens is you lose static friction, and what type of friction does it go into? Kinetic, because that's what we call that slipping, right? That slipping is happening. And which way does kinetic always go? The opposite of the way the object's moving. Can you control your car when it's slipping? Absolutely. All right, let's move on to another example. That was hopefully helpful for a few problems, but let's go back to the Frodo example that we were finishing yesterday. What mass did we decide Frodo was going to be? What's that? 223 newtons. That's oddly specific. All right, fair enough. 223 newtons, okay? It's not his mass, though.
Mass is,
That would be his weight.
yeah, 22.7 kilograms.
22.7 kilograms. That's right, because I actually had you work backwards from weight, didn't I? All right, and what do we decide the angle of the hill is going to be? 15 degrees? All right. And the question is, how much does he accelerate? All right. So we have Frodo on the hill. What's the force diagram of Frodo on the hill?
Force gravity down.
Force gravity down.
Force normal at the angle of the hill.
Force normal. Perpendicular. What'd you say? Did you say force normal?
Yeah, I said force normal, just said that.
Perpendicular to the hill.
Yeah.
And
Force friction.
force friction. I meant force normal. A little large there. Okay. Now I'm going to draw something up here that we don't usually draw up here. Okay? And you shouldn't usually draw up here. If you've been drawing it up here, no harm, no foul. Let's fix it. But no big deal. Okay. Acceleration. Which way will Frodo accelerate here? Be a little bit more specific, because you're saying to the right? Down the hill. Now, as I draw that picture, if I draw that arrow, okay, just using basic understanding of vectors, you can see that's in what quadrant? 4, correct. So, is there an acceleration in the x with that particular? Is there an acceleration in the y with that one? Yes. This is going to make things very messy. Okay? Now, I don't like just to tell you it's going to be very messy, so I did the work. Okay? I don't want to show you how messy it is, and I'm just going to show you that. We don't need to do it at all. I just want to avoid the mess. You know, before we do that, here's what I want you to do. Okay? Let's take a step back. Let's just do the sum of forces as though we were going to continue this like normal. Like, what is the sum of forces in the x? Just as an opportunity for practice here. What is the sum of forces in the y? Go ahead and do that real quick. Take a minute or two. If you struggle with it at all, please use your group as a resource. See what they're doing. Ask them questions, or ask me questions. Ask questions. Ask questions. Ask questions. Intelligent people ask questions. Why do we think everybody uses CDs? I mean, there's so many options for wheels. And sorry, what's up?
What were the 3 questions like to go off of when you're determining?
Excellent question. Okay, is it in the y? So talking about the y, whatever it is. Okay, which direction is it, and is it only in the y? So if I'm looking, for example, at force normal right now. Also, I notice I didn't label force friction here. If I look at force normal, the answers to those, we're doing x first. Okay, so we'll do x. Is force normal in the x? Actually, it is, because you see it's going, it's like up and right. So it's both up in the y and in the x. See how it's pointing right? So the only arrow that would not be in the x would be straight up or straight down. Okay? So the fact this is, I'm not saying just straight right, but we can see it's a little bit right. Yes? Okay? So we would say there is force normal in the x. Okay? We would see since it's going right, we would say it's positive. And we would say, as we just said, it's not only in the x, it's also in the y. So we would say positive force normal in the x. Okay? And just continuing along with this, is friction in the x? Yes. It's left, so it's negative. Is it only in the x? No. Okay? And gravity, is it in the x? No. So we're done with sum of forces in the x. And then the question is this accelerating in the x? Yes. Okay. Summing the forces in the y. Help me out. What are the forces in the y? Positive force normal in the y. Positive force friction in the y. Minus force of gravity. And is it, we're done there. Is it accelerating in the y? Yes. Okay. Now, to look at this problem, here's why this problem is ridiculously icky. Force normal in the x and force normal in the y are not the same variable at all. They're entirely different things. So if I look at the things I don't know, 1, 2, 3, 4, 5, 6. If you have 6 unknowns, what does that require to solve? Yep, 6 equations. Here it is solved. I'm sorry, I didn't get all the way down there. It's icky. And that is your final answer at the bottom there. Okay? Acceleration is equal to gravity divided by the cosine of theta times the quantity cosine of theta plus mu times the sine of theta divided by the quantity sine theta minus mu cosine theta. All that plus the sine of theta on the bottom. I don't think you want to do that. Nobody wants to do that. Let's not do that. All right. So let's go back. What caused that to happen? What's the issue? Now, before I get too far here, try to remember to correctly save myself a picture. Next slide. Cool beans. All right. The issue with that is how we set up our axis. But if we go all the way back to chapter 2, who decides the axis?
You do.
We do. Correct. Like, you might not have realized this, or maybe you did realize this, but I don't think anybody asked here, so I apologize if I'm repeating myself. If you're here last night, I'm definitely repeating myself, but I kind of have a whole rigmarole. Why didn't we do 3D kinematics? We did 1D kinematics. We did 2D kinematics. Spainhour does not strike you as the individual who would lean away from something because it was too hard. We just figure it out and move on. So why didn't we do 3D kinematics? Well, it's real simple. If I say that this way, in here, pointing horizontally is the x, then that makes this way the y, and what's the third dimension? The z comes out at you in this particular direction. If I throw the ball at red, did the ball move in all 3 dimensions? Yes, it did. Did it move in the x? Yeah, it went that way. Did it move in the y? Yeah, it went up and down. Did it move in the z? Yeah, it went that way. That'd be, and why did we do 3 dimensions? Well, who made it 3 dimensions? I did, we did, when we set up the problem. Watch what we can really simply do with the x. All right, now, is it still operating in the same situation? Is it still in the x? Yes. Is it still in the y? Is it in the z anymore?
No.
Because of how we simply set up the problem. Literally make the direction it's originally going the x, you eliminate the z. We don't need to do 3 dimensions, we don't need to add extra complexity here, okay? Who made this in 2 dimensions? We made it a 2-dimensional problem by setting up our, how? Just again, how? By setting our x-axis in this standard way. Do we have to set the axis in that standard way? No. We decide where the axis goes. So I'll just tell you what we're going to do to try to make it simpler. And once again, I'm going to go ahead and go back and put up acceleration up here. I shouldn't do it, but I'm gonna, okay? I'm gonna put acceleration back up here. Here is the goal, and this is very important for, again, later in the year when you're gonna see something similar, but you won't do this, okay? What you wanna do when shifting the axis is make the acceleration on an axis. I'll say that again. What you wanna do when shifting the axis is make the acceleration on one of the axes. Okay? Other nice things will happen because of this, but they are not the goal. Not the goal at all. In other words, over here I have positive x, and up here I have positive y. What I want to do is I want to take this x-axis and match it here. So what you want to think of is, all right, this angle is with the horizontal. And I go back to some basic geometry here. If these 2 top and bottom lines are parallel, if that angle with the horizontal, if there's an angle with the horizontal there, then this angle is the same. Yes? Every angle with the horizontal, which means if this is 15 degrees, then I'm going to shift this down 15 degrees. Does that make sense? Okay. If this came down 15 degrees, what's this guy going to do? It's going to go up 15 degrees. What's this guy going to do? What's that? Go right 15 degrees. And, okay, this is an important distinction. Please notice that gravity and the axes are pointing the same way. Which of them are we moving? The axes. You can't move the direction gravity goes, but you can move the axes over 15 degrees. Now, what this looks like, you go, Spainhour, how am I going to like do this math every single time? You don't have to, and here's why. When moving this down 15 degrees, what you're going to notice is that this axis is now, another way to look at it, is that it's now parallel to the surface. Yes? And then the next axis is going to be then, by definition, perpendicular to the surface. So when I draw my new axes, here's what I do. I look at this picture right here, I draw my force diagram first, and then I go, hey, friction is parallel to the surface. So I'm going to draw that axis parallel to the surface. And this one's perpendicular to the surface. So I draw this one straight through friction, this one straight through normal. And then the only thing you have to keep track of then is this. Where did that angle go relative to the force of gravity? Well, we just saw it a second ago. The y-axis did what? It shifted left 15 degrees. So this angle here is 15 degrees. We good with that? All right. With that, let's go ahead and sum the forces again. Now, I really don't care about this next part, okay? But there is something that some people like to do with this that I'm fine with or am not fine with. We have either option. I will do either one, and it's this. Rather than continue saying x and y, you certainly can if that's easier for you. If you don't want to switch that at all, go ahead. Some people prefer to call this new axis, instead of x, the parallel axis, and this one up here the perpendicular axis. In which case, instead of summing the forces in the x and the y, you would sum the forces in the x would be the parallel, and you'd forces in the perpendicular. If you don't like that, if that just makes you go, ooh, that's, well then, all you're gonna do is, you're gonna keep your old school stuff of x and y. I don't care, I really don't, but just to be consistent, my personal preference is using parallel and perpendicular. So I'm gonna do them now, but if as you're practicing these, you find x and y to be easier, and all of you guys come back in here and like, yeah, we all want to do x and y, I will happily do that one instead. Okay, so let's sum the forces either parallel or in the x now. What are the sum of forces parallel now to this new, it's kind of, you got to shift your way of thinking here, but like, okay, what are the forces going this way? I did not draw this perfectly at all, I apologize. My force normal, I think, is a bit off, but all right, what do you got?
Force gravity.
All right, so let's start with force gravity. It started with the weird one first. Okay, force of gravity. So ask always the same questions. Is it traveling parallel? Yes. Okay, it's right here. Okay, or if you prefer, up here. But yeah, it's going parallel. Okay, is it positive or negative in the parallel or the x? Positive. Okay, is it only in the parallel? No. So we would write this as positive force gravity in the parallel, or if you're doing the old school way, in the x. All right, next, anything else? Minus force friction. Yes, minus because it's going back, but now this is the nice thing that happens here. Is this only in the parallel? Yes. Unlike the last one, where friction was split up in the x and the y, because it was operating in both, it no longer is. It's acting, I said, parallel. Is there anything else there? No. You'll notice that force normal now is entirely perpendicular. So again, another nice thing, it's not acting in both. Is it going to accelerate parallel? Yeah, if I go back to drawing that acceleration that I keep telling you not to draw, that's exactly the direction that it's in. All right, let's come over here. What's the sum of forces in the perpendicular? Okay, any friction? No. Is it accelerating in the perpendicular? That is actually quite literally the reason why we did it, is so that this can be 0. And if that is 0, that means that force normal and force gravity perpendicular are equal. This logic right here is actually, and I apologize if you struggled on it, and this line of logic is literally, I think, on 4.5. I think it's number 4 or 5, the one where the object's on the hill and you're supposed to figure out force normal on all of them. It's literally this right here is what you have to do. All right, so how do we get force gravity perpendicular? Well, basically it's just a triangle. What is force gravity always equal to? Mg. If you prefer to calculate that early, feel free. I'm just going to treat mg like it's the hypotenuse. Now, the perpendicular, this one right here, is it adjacent or opposite? This one right here, oops. So here is force gravity perpendicular. Let me blow up this triangle a little bit bigger for you. Here we go. So here's force of gravity, that's equal to mg. There's my triangle. It's a little bit weird because it's on the side. Notice my 90 degree is right here, so I can use trig. But this is force gravity perpendicular, and my angle is right here. So is this adjacent or opposite? Adjacent. So to get force gravity perpendicular, it is mg cosine of 15 degrees. Now, I'll tell you the truth. My usual technique is to just hold variables for as long as possible. I know that makes some of you guys uncomfortable with numbers and all that. So for the sake of you right now, I'm going to do it. I'm going to continue with mg cosine 15 usually. But if you prefer, what is that? The Frodo was, oh, I had it on the other page, didn't I? Thank you. 22.7 kilograms times g times cosine of 15. What'd you get? Okay, 214. Let's just go ahead and round that to 215. Did I give you a mu yesterday? I don't know if I did.
No, you didn't.
I did not. Let's go ahead and make one up real quick. Based on what you saw on this surface, this is a fairly slick surface. Just make up a mu, I really don't care. Mu's, by the way, I don't know if I told you this, range typically between 0 and 1. The highest mu that is regularly recorded is, oh gosh, what's it called? Velcro. Velcro gets up to like 2.5, okay? That's about as high as it's ever gonna get. But most mu's in a room like this are almost always somewhere between 0 and 1. So a very slick surface like ice is like 0.05, okay? A sticky surface like orange juice on the counter can get as high as like 0.7, 0.8. But, so, his face on rock, what do you got? 0.6, beautiful. All right, that being said, let's continue the problem. So what are we gonna do with force normal now?
You're gonna find force of friction.
Yep. Force friction is gonna equal mu times force normal. So that 0.6 times 215 newtons. Whew, 21.5, 43 times 3, 129.
Yep.
Okay. All right. And the rest of this is pretty easy. Now all we do is we plug and chug into here. How do we get force gravity that's parallel? Yep, just trig. Right over here is force gravity that's parallel, so it's going to be mg since it's the opposite sign. So mg sine of 15 minus force friction divided by mass gives me acceleration. Mass is, what'd you say, 22.7 kilograms times g times the sine of 15 minus 129 newtons divided by 22.7 kilograms. The acceleration should be negative 3.15. Now, in this case, I'm going to say I'm completely fine with this negative acceleration, unlike the acceleration at the very beginning of today. Why is that? What does that acceleration, negative acceleration, mean Frodo is doing as he slides down the hill? It means he's slowing down. It means he was already sliding on his face down the hill. His velocity was that way, so a negative acceleration means he's coming to a stop. Why am I okay with it in this case and not the jug? Because we're dealing with kinetic friction, not static friction. Is it possible for kinetic friction to cause an acceleration to bring something to a stop? Yeah, 110%. Here, I'll demonstrate. Did kinetic friction just bring that to a stop? Can it do it on a hill? Sure. Which number up here is probably the most likely that is a little bit off, okay, if we think that he should be speeding up down the hill? Which number that we started with here is probably the most likely to be off?
Mu.
Probably mu. Probably mu is a little high. Yeah. And I told you to pick one. That's not a fault. That is just to say that if you're looking at this and going, that ground seems a little bit sticky. Okay? That ground seems like it's causing more acceleration than I would expect it to. It's more than likely because the coefficient of friction is a little bit actually lower than what we planned, which is not bad for the problem at all. Just gives you an idea of context of what you're looking at. All right, let me tell you one last thing and then I'll be done. The last thing I want to tell you is this. It is Spainhour's pet peeve. Spainhour has pet peeves. You've heard them before. One of the other ones normally is magic math. Here is Spainhour's major pet peeve. This is how you should draw it. How you should draw it is the correct force diagram first, and then shift the axes. I am completely okay with that. This is how it works. Here's what I am not okay with. And I understand that it's more comfortable, but it is absolutely incorrect for your brain and moving forward. Do not shift the axes, and instead decide to shift the forces. Gravity does not go down and to the right, okay? You can change how you look at a problem. You don't get to decide what the problem actually is. That's a context that will reach far beyond physics as far as our understanding of the world surrounding us. We can change how we decide to look at the problem. We don't get to decide what the problem is. So, doing this means you're sticking with what's comfortable and not pushing your brain to better understand the situation. So that is an automatic taking off all the points on the force diagram. I don't care how right it is and how right the rest of your problem is. Okay? So again, draw the force diagram correctly, shift the axis. That's what I'm looking for. Do not shift where the forces go.